tensor of inertia. So based on this spherical harmonic expansion of this, which we have, we can write that the second degree harmonic, let me write it again, spherical harmonic expansion. I will put GMR because I want to have this the spherical harmonics as it is in the gravity model from M0 up to 2, and I write cosine M lambda Cn M2 bar. Bar means the fully normalized. Then you get it from the model directly. These are the things that they are available to in the model. M lambda and P2M cosine theta. This potential actually is a potential of degree 2. It can be written in this form, 15 GM R2 over 2 phi. If I put this formula and these things and simplify it, I come to this one. R is a vector, the quadratic form, and this Q is a tensor, and is R is the position vector again. This T is transposition. In this quadratic form, or the tensor Q will be, if you simplify it, takes time, but this, the sign coefficients of the gravity field, of course the fully normalized one, S22, C bar 21. Here we have S22 again, minus C22, C20, 3, S bar 21, C bar 21, S21, 2, C20, and 2. So this is a cube, and it is presented inside the Earth's coordinate system. Now, if I change this coordinate system to the inertial coordinate system of the Earth, this tensor will change. Inside the inertial coordinate system, this potential is 15 GMR2 2R5, and inside this system we have another Q which presents the mass distribution actually inside that. So this Q tilde will be very similar equation with that one, but this A and they are not the same as those in the gravity field. These are other types of harmonics. As you see, this tensor of inertia here is diagonal. Unlike this, unlike the, so this is the diagonal form of this in the inertial coordinate system, which is defined based on the mass distribution of the Earth. So we can determine the eigenvalues of this matrix by this formula. Eigenvalues. Eigenvalues are, let me see, this is E is the unit matrix or identity matrix, and determinant is 0. This eigenvalues has been solved already by Marchenko and Suvinzer in 2003. I just write the result. We have 3 eigenvalues of 2, P3 sine phi plus pi over 3, 2 minus 2 P over 3 sine phi 3, and the third one 2p3 sine phi minus pi over 3. So it seems simple, however, we need to know this phi, p, phi and p, and if you have q now, it will be phi and p. So what are they? P is simply a quadrat, quadrat of summation of the all these spherical harmonics of degree 0 and 2. C22 square normalized and S22 P. And phi here is not latitude, be careful, is sine 3 by 3 divided by 2p divided by q. You compute p and put it here. And also you already have p here. And the q has a long formula that I write it here for you. So q is 2c20, 3 over 3 plus. You see, all of them are related to the 0 and first degree harmonics of the gravity field of the S21 plus S21 plus quadrat 2c22 quadrat minus 2 S22 quadrat. And I continue this down here. Plus C22 C21 S212 plus, oh my god, very long, S21 CS22. So when you computed these spherical harmonics in these coefficients, then you can simply make this matrix a Q-bar matrix. And this the method of the diagonalization. This means that you can compute these diagonal elements and put it on this matrix to get. This is called diagonalization in linear algebra. And it is not very difficult to conclude that epsilon 1 will be the A22 bar minus A20 bar over square root of 3. 2 will be minus A22 bar minus A20 and 3, and epsilon 3 to A20 bar. So the question is that, okay, so far I have I could get these epsilon values from the Earth's gravity model. And now I'm going to compute this A22 and A20 to come to the dynamic flattening. So if from this one, I can simply compute 20 from that. And if from this one, and also if I combine these two equations, I can come to these two new equations that I write it here. A bar 20 will be square root of 3 and 3 over 2. And A bar 22 will be epsilon 1 plus epsilon 3 divided by 2. So now I connect this A20 to this the constant terms of the tensor of inertia. So let me see. A20, which I have already determined from the eigenvalues, will be A, B, C, C divided by 2 square root of m, mass of the Earth. Then A22 bar will be B minus A 2, 5, A2M. And dynamic flattening, dynamic ellipticity of flattening, so C B divided by 2 divided by C. So based on this, if I solve these three equations, because A20 is noun, A22 is noun, and if you assume that H is noun from astronomical observations, and I solve these equations, I get A as B or true, or A2, R or A is the same here, 1 over 1 H. A bar 20, A bar 22, and then B is 5M A2, or A is the same with R, big R, radius of the Earth, and A bar 20 plus A22 bar is 2. And C, I will write it up here. Minus 5 M A2, A20, and H. So you have learned before how to what's the relation between the dynamic flattening and the changes of the C20. So you can connect the relation and compute the dynamic flattening from the gravity and put it here to get C. And when you have the dynamic flattening, you can put it in here to get A and B. Also, you can compute the eigenvectors. And eigenvectors, which shows the direction of the inertial coordinate system of the Earth. And these are these eigenvectors. I will write it Li, Mi, and Ni. Eigenvectors, vectors. And also there is a long derivation for finding this eigenvector, but I write the results for you so you can see the whole process, that how they are connected to the gravity field. That's the goal. They define first UI. UI is C21 bar. You see C21, 22, which are all inside the gravity model, and I could be 1, 2, or 3, 2, 0, radical, the square root of 3, and 2, 2. As you see, they are all 0 and second degree harmonics of the Earth's gravitational potential. So if you compute this, if you have a gravitational potential or gravity model like EGM08 or any other gravity field model, you can compute UI, and from UI you can compute N, the third eigenvector, which shows the direction of this inertial coordinate system, and S21 bar. And again, you see eigenvector comes here, plus 2 C2 bar 0 divided by square root of 3 divided by C21, the whole 2 and the whole 2. And now we go for M and L. And M will be simply UI NI, and Li will be Ni divided by C2 bar 1 epsilon I minus 2C20 bar UI. So it depends if you want the first vector, second, or the third one. So based on this eigenvectors, you can compute latitude and longitude of the points that this vector are the axis of the inertia coordinate system is pointing to. Lambda I for the first axis is arctangent mi over li, and the colatitude will be again arctangent ni over li to mi2. So in this way you can, if you have the sphere here and you have this coordinate system, for example x, y, z, in this case you can determine the position of the rotation axis of the, not rotation, the axis of the inertial coordinate system. I will write z xi and yi. So these points, the coordinates of these points over inertia, this angle. So this is the way to determine the inertial tensor, or determining the inertial coordinate system of this. And you can simply use the time variable gravity fields to determine the variations of this.